I've designed a ventilator. You can set pressure, volume, respiration rate, IE ratio, and PEEP. It'll accept oxygen. You can build it for $50 at scale out of parts you can find at any large hardware store. You can build 1,000 a day, every day, in any city on Earth with parts you have on hand, starting right now. Conservatively, in the next year, 50 million people are going to die, and a lot of them are going to die because we don't have enough ventilators for them. As far as I'm concerned, the two biggest things we can be working on right now are a cure and building ventilators. Consider this design a place to start. Everything in it is essential. You can add to it, but you can't take anything away. At its core, it's simple and mechanical. What that means is it doesn't have a complex supply chain. It doesn't need valves from Italy and computers from China. It doesn't need flow sensors or alarms. You can add those things in, and I'll show you where, but all it relies on is physics and gravity. Even if the whole machine doesn't fit your needs, there might be something here that can help you. Maybe it's the valves or the way we move the air or how you set the settings. The point is, if there's something here you can use, take it. Discard the rest. And remember that the key design constraint of a ventilator is to ventilate, and this machine will ventilate. I'm posting this video earlier than I'd like. In a perfect world, I would have a completed machine to show you at the end, but that's not the case here. Some of this is still on paper. My gut tells me that the valves are the most valuable part of this design, and those have been built and tested. That's why I'm posting early. Anyone who's trying to build a ventilator is going to have to solve the problem of the patient valve. It is complicated. I had to go through a lot of iterations to wind up where I wound up. My valve is simple and reliable, and you can build it for $3 out of hardware store parts. Now listen, I believe in it, but please don't try to save a patient's life with it until it's been verified by other people. I'm going to walk you through some concepts of ventilation, then I'm going to walk you through the machine and valves, and then construction. Before I do that, there's a few other things I need to say. First, now that this is posted on the internet, everything you see here is prior art. That means it's not patentable. So if there's something helpful here, please take it and use it. I'm not trying to make $1. I think it's gross to try to profit off human misery. If you think I can help you, please contact me. There's a link in the description to do that. I don't care if you're from Arkansas or Italy or Iran. If I can help you, I will try to help you. If you want to make one of these or 100 or 1,000 or a country full, please contact me. If you have feedback about the machine, if you think I missed a nuance of physiology or ventilation or physics or engineering, please contact me. This is a thing that we can make better together. If you want to contribute, that would be awesome. You can use the form. Also, there's a GitHub link in the description that has design resources. It has CAM profiles and spreadsheets and everything you'll need to evaluate the machine. You can also open an issue there or a pull request. There's a lot more to be said about this. Not just the machine itself, but about how we could build them at scale, how it would be integrated into an existing medical practice. And I don't have time to say all those things. I have thoughts about them, and so there's stuff that's going to be left out. If you have questions for me, please contact me. We can talk about it. Thank you for making it this far. Stay healthy. We can all get through this together. So first things first, I'm a great engineer, but I'm not a great artist. So I hope you'll bear with me with these illustrations. The concepts are good. The drawings are less good. Okay, so this is an idealized ventilator circuit. There are settings you can set. We'll just imagine that we can control these magically. And then this is a magic valve. Ignore the fact that air could just go from the inhale to the exhale. We're going to control that in a later step. So just imagine air comes in this way and goes out this way. So I'm going to walk you through the settings. The inhale step is when we're pushing air into the lungs. And the exhale step is when we stop pushing and let the lungs deflate to whatever the pressure we want them to deflate to. So we push and then we stop pushing. That's the fundamental way a ventilator works. Okay, so on the push step, we need to be able to set the pressure, which is how hard we're pushing air, the volume, which is how much air we're pushing, breaths per minute, or respiration rate, which is how many times a minute do we push and stop pushing, how many times a minute do we inhale and exhale for the patient, and then the IE ratio, which is what percentage of a breath is inhale to exhale. If it's pushing, that's the I, the inhale, and if it's not pushing, that's the E, the exhale. And it has nothing to do with an absolute amount of time. A 1 to 2 IE ratio isn't 1 second pushing, 2 seconds not pushing. So if you have a 1 to 2 IE ratio, it'd be pushing for a third of the time and not pushing for 2/3 of the time per breath. That's all the IE ratio is. It's just what percentage in every breath are we pushing and not pushing. PEEP is just how much pressure are we going to maintain in the lungs on the exhale. So it's pretty simple. It's pressure and volume, how hard and how much air, how many times per minute do we do this cycle of push and release, and then what's the ratio of how much we push to how much we release every time we do it. Then on the exhale, it's how much pressure do we leave in the lungs. And this value could be 0, by the way. This pipe could just go out into open air. So we push air into the lungs and we just let it escape. But alternatively, you can set this to a higher value to maintain some pressure in the lungs at the end of an exhale. Okay, so the first thing we need is a way to move air, and we need to be able to set the pressure and the volume of that air. So there's lots of ways to move air. We could use a compressor, we could use pistons, but the simplest air pump that I can think of that's reliable and has pretty loose tolerances is a water air pump. So you can try this at home. You can take a bucket, fill it with water, take a 2-liter bottle, cut the bottom off, take the cap off, and then push the bottle into the water, pull it up, push it down, and if you put your hand near the top, you can feel that it's pulling air in and it's pushing air out. Because when you pull the bottle up, you create vacuum, and that sucks air into the bottle, and then when you push the bottle down, you're reducing the volume in the bottle, and that pushes air out. Super easy, works, super reliable. It doesn't need gaskets, it doesn't need lubricants. It's just an open pipe moving up and down in water, pushing air. So in this system, the way you control the volume of the air is just how much you move up and down. If you move up a little and down a little, you move a little bit of air. If you move up a lot and down a lot, you move a lot of air. So great. With this simple system, we can set volume of air based on how far we move up and down. Okay, so in order to make that an air pump, we need to be able to capture the air that comes out of it, and we need to be able to move air through the system in one direction. This is a simple way to do that. I've introduced a new symbol, which is this C. This is called a check valve. They're commercially available. I'm also going to show you how to build one. But all a check valve does is it lets air move one direction, but not in the other direction. It's indicated by these arrows which direction the air can move through these valves. Here, in this system that I'm going to show you, the air can always move to the left, but it can't move back to the right. Great, so if we take our chamber that we were moving up and down and we put a T on top and we add 2 check valves, we can bring air in from one side and then push air out the other side. So if this is a pipe, air is going to move this way as we move up and down. So this is a simple depiction of that. When this moves up, it creates vacuum, and it's going to pull air in from the right-hand side because air can't come in this way into the system because of this valve, but it can come in this way from the system, and this is to the open air. Okay, now this is same system but different direction. Same check valves, same ability for air to move this way, but not this way. This chamber is moved up, so this is filled with air that's coming from this side. And now when we push it down, it reduces the volume, and air wants to move out of the system, but air can't move back through this check valve, but it can move through this one. So when we push it down, air goes this way. As we move the system up and down, air comes in from the right as we move up, and when we press down, air goes out through the left, through that tube. Now we have a simple air pump, up and down. And again, volume is set by how much we move. We move up a little and down a little. We move a little bit of air. We move up a lot and down a lot. We move a lot of air. All right, so we have a way to move air, and we have a way to set the volume of the air that we move. And now we need to be able to set the pressure. First thing you need to know is that this system moves freely, in that you can pick it up and let it go and it just drops, right? There's no rigid support as it's drawn. So it has a weight of its own. So if you lift the system up and you let it go, it's going to fall, because of gravity. And the amount of force it falls with is proportional to its weight. Setting pressure in this system is actually pretty easy, it turns out. You just add weight. And the more weight you add, the higher the pressure of the air that comes out of this system. So the pressure of air that comes out of this system is the weight times the cross-section of this pipe. It turns out that there's a magic number. So if the inner diameter of this pipe is 3 inches, then it's 0.1 pounds for every centimeter of water of pressure you want the air to have. Centimeters of water is a unit of pressure measurement that doctors use on ventilators. PEEP is set in centimeters of water, as well as the pressure of the air coming out of the ventilator. All the pressure settings on a ventilator are set in centimeters of water. So there's a magic value, and that magic value is if the inner diameter of the pipe that reciprocates is 3 inches, then for every 1 centimeter of water of pressure you want this air to have, you add 0.1 pounds. If you want to have 20 centimeters of water pressure, this section needs to weigh 2 pounds. If you want 15 centimeters of water air pressure, this section needs to weigh 1.5 pounds. If you want 10 centimeters of water, 1.0 pounds. 2 centimeters of water, 0.2 pounds. It's really easy. Take your centimeters of water, divide by 10. That's how many pounds you have to add. Now there's a nuance here, and that's not the weight that you add on the top. That's the weight of the entire free-floating system, right? So if you take this weight off, all of this plumbing and valving and piping, it's all going to weigh something. And that turns out to be a really important design constraint of this system, because pressures that doctors set on a ventilator, the pressures of air that come out, anywhere between, say, 8 centimeters of water and 30 centimeters of water of air pressure. So that means anywhere between 0.8 pounds and 3 pounds of this entire reciprocating system, including all the plumbing and everything that's not affixed to the machine, everything that you would lift and drop to move air, that's the total weight we're talking about. So there's a couple ways to handle this situation. You can try to make this section as light as possible, all the plumbing. The easiest way to deal with this, in my opinion, is somehow to have this section have a negative weight, to have it float in water. And then when calibrating the machine, you would weight this section until it was neutrally buoyant, right? Until it weighed nothing, essentially, in the water. And then you would add however many 0.1 pounds you want to get to the centimeters of water pressure that you want. There's a few ways to do this, but I actually came up with a clever engineering solution to this. And that is, you can come up with some complicated buoyancy system. You could glue foam to the bottom of the pipe, or you could maybe put an air balloon in here like a ballast. But all of those things seem complicated and prone to failure. It turns out that there's a type of pipe called ABS foam core. It's widely available. It more than handles the pressures we're talking about. It comes in 3-inch inner diameters. And the coolest thing about it is it floats. That means if we're smart about how much ABS foam core we use in this center section, it can make up for the weight of all of the plumbing, and this thing will actually be positively buoyant. There's no ballast to fail. There's no complicated parts. It's just an inherent characteristic of the materials we chose to use. So that's fantastic. It turns out, given the weight of all this plumbing and the design, you actually need a fairly tall piece of ABS foam core. In the design you're going to see later, the outer 4-inch pipe is 48 inches and the inner foam core pipe is 42 inches. So pretty tall, but in the scheme of things, manageably sized. Great, so now we have a system where we can move air and reliably set volume and pressure. We're well on our way. We're back at this picture because I need to talk about the patient valve for a second. Patient valve is really important, and what it does is it allows high pressure air from the ventilator to move into the patient's lungs, but then when the ventilator stops pushing, it allows the air from the patient's lungs to take a different path out of the system. The other thing it does is it controls which direction the flow goes, and it shuts off the flow to the PEEP when you're pushing high pressure air. Because if you look at this valve, if you just added a bunch of high pressure air into the system, it would just go right out the PEEP. The lungs wouldn't fill, right? Because this is just open to the open air. So why would it go into a area with more restricted airflow? It wouldn't. It would just go through here and then come out this way. So the patient valve needs to close off that bottom section when air is moving in, and then when the ventilator stops pushing, it needs to open and let air come out a different path. That's really important. The other thing to know about the patient valve, which is a key design constraint of a ventilator, is you need to put this valve as close to the patient as possible. So let's say instead of that last image, this is what we built. And the problem with that is when you push fresh air in, this fresh air isn't going to make it all the way to the patient. It's only going to make it halfway down. So you are going to push air into the patient, but you're going to push the stale air that was in this section. So that stale air is going to get pushed into the patient's lungs. And then when this stops pushing, that stale air is going to come back out and fill that section of tube. And then when you push again, that stale air is going to get pushed back into the patient. And when you release the pressure, the stale air is going to move back into the tube. And you're really just going to be moving this end section of air. This dead space is going to move in and out of the patient. And the problem is that air is going to quickly deoxygenate, and it's going to quickly get high CO2, and it's going to fucking kill the patient. What you need is to move this valve as close to the patient as possible so that when you push fresh air, there isn't much dead space. That fresh air fills the patient's lungs, and on the exhale, there's not much dead space, so that air moves out. And while there will be some dead space in this pipe, it'll be a lot less than the volume of their lungs, and so every iteration of this, they'll get more oxygen. Now we need that magic patient valve. This isn't exactly how it works. I'm going to walk you through building one later, but I think this is a good mental model. This is like a little door, and this is a spring. High pressure air is going to move in from the ventilator. So this door closes over, seals that bottom section so you can pressurize this whole system. Then when the pressure stops, that spring's going to move the door back up and allow the high pressure system over here to escape out into open air or to your apparatus that allows you to set the PEEP. This is a patient valve. This is a very difficult engineering challenge to solve, and I figured out how to do it for $3 worth of hardware store parts. I'm going to walk you through that in a little bit. Okay, so now we have a way to move air. We have a way to set the volume of that air and the pressure of that air. We have our patient valve that allows us to push high pressure air into the patient and then allows it to come out a different way. So there's three things left. We need to set respiration rate, IE ratio, and PEEP. PEEP is the easiest to set. I mentioned earlier that PEEP is set in centimeters of water of pressure. That's the unit. And there's a really cool symmetry in this system. The PEEP is set literally in centimeters of water. So if you run your exhaust hose out and into a container of water, and you graduate the pipe in centimeters, the number of centimeters you put this pipe into the water is the centimeters of water of pressure that the PEEP will be set to. It's important to know that it's based on the depth of the pipe in the water, not the depth of the water. So it's measured from the water line to the bottom of the pipe, not from the bottom of the pipe to the bottom of the water or something like that. So the only other extra piece here is this check valve, and it's not strictly necessary for the PEEP to work, but in the event of failure and a vacuum in this part of the system, you don't want to suck water back up into the system. That feels like a thing that would end very poorly. So now you can set volume, pressure, and PEEP. Now we just need respiration rate and IE ratio. Okay, so we have a system now where you can set pressure, the amount of weight of this reciprocating system. You can set volume, the amount you move up and down. You can set PEEP, which is the centimeters of water. Now we need to set respiration rate and IE ratio. Let's talk for a minute about the mechanics of this. This cam will rotate, and when it rotates, it'll lift this set of forks up. That'll lift this whole center system up. Then when the cam starts to come back down, the forks move out of the way, and this system is allowed to fall. It's important to note these two, they can only lift. They're not connected at the top, so they can't pull the system down. That's important because if this system was pulled down mechanically somehow, with more than just its own weight and gravity, it would provide a higher pressure than you intended. This system is only providing air pressure when it's unsupported by these forks. That is, when the forks are out of the way and this thing is falling under its own weight, accelerated by gravity. When this system isn't falling, it's not providing pressure. And when it's not providing pressure, the lungs are allowed to exhale normally out into the PEEP. So the IE ratio in this system is controlled by how much we're falling, which is the inhale step, to how much we're not falling, which is exhale. You can cut this cam to produce lift half the time, or to produce lift a quarter of the time, or a fifth of the time, and I'll show you cam profiles later, but just trust me that you can cut this circle to provide whatever mechanical movement you want to provide. So the IE ratio is provided by the shape that this cam is cut in. Great, so now we can set pressure, we can set volume, we can set PEEP, we can set IE ratio, and the last thing we have to worry about is respiration rate. And that turns out to be the easiest thing of all. So if you have a variable speed motor, respiration rate is how many times a minute does this cam go around? Because you got to remember the IE ratio is baked into the cut of the cam. So if the cam turns once in a minute, you have 1 breath per minute. If the cam turns 10 times per minute, you have 10 breaths per minute. If the cam turns 20 times per minute, that's 20 revolutions in the right ratio of up to down, and that would be 20 breaths per minute. Couldn't be simpler. So we're done. We can set pressure, volume, IE ratio, respiration rate, and PEEP. This is a ventilator. Now there's a couple other things to note. You could add oxygen on the fresh air side, and it'll just flow through the system. You should also add a filter on the fresh air side to prevent particulate matter from getting in. You may want to put a filter on the top of the PEEP as well. So there you go. So now I'm going to walk you through construction of the valves and then construction of the entire machine. The system's completely mechanical as I've shown it to you, but I wanted to show you where you could add some sensors if you wanted to. So you'd need a microcontroller, but you could pretty easily, I think, detect the water levels. I think you could probably just run 2 strips of copper tape up and down, and then hook 2 leads up to it and just measure the voltage difference between them, and that's going to be dependent on the water level. If you wanted to, you could put some LEDs on the outside that you could then individually address, and so if this whole thing wasn't clear, you could display on the outside the water level based on the resistance. Also, you could have an alarm if the water level dropped too low. The other thing you could add is a flow sensor, and you would want to put it here in this part of the circuit between the patient valve and the patient, because you want to be able to detect flow into and out of the patient, both volume and just to detect that flow is actually making it in and out. You could add an alarm to let you know if for some reason this stops working or if the water levels get too low. I do want to point out, I think you could integrate this machine without the alarms into an existing medical practice. I don't think it would be easy, but I think in a dire emergency situation, you could just train lay people to monitor the machines. When this moves up, bubbles. When this moves down, no bubbles. When this moves up, bubbles. When this moves down, no bubbles. If anything different happens, the machine is broken. Also, I think the redundancy plan for these is pretty straightforward. I think they're cheap enough and easy enough to build, and you can build enough that if you have a layperson watching it and it breaks, you just tell them to swap it out immediately for a standby machine, and then tell somebody. And then you can fix the other machine because they're simple enough. Just for the sake of completeness, I'm going to talk about a couple bad states that this system can get in, and how to mitigate it. Although I don't think that these are very likely, but I think it is important to think about this when you're building it. So you have to remember, this center section is going to be moving up and down regardless of what happens with the rest of the system, because it doesn't have any feedback. So it's going to move up, and it's going to drop, and it's going to move up, and it's going to drop, and it's going to do that on some consistent schedule, no matter what happens with these valves or anything else. Now, the way it's designed, it'll never exceed the pressure you expect it to push,
and it'll never exceed the volume you expect it to push, but you could get into some kind of weird situations depending on if these valves break and in what order they break. Okay, so the first bad state I'm going to talk about is one in which you wind up with a vacuum in this part of the system. So this check valve breaks closed, or there's a blockage, preventing air from moving into the system. This moves up, creating a vacuum. This check valve should prevent vacuum in this part of the system. It'll just be a vacuum in this container. That said, if this check valve then breaks open, so this breaks closed or is blocked, a vacuum is created. This check valve breaks open, allowing the vacuum to try to satisfy itself on this end of the system. You're going to suck air out of the patient's lungs. Now, presumably the amount of volume in the patient's lungs is less than the volume that the system wants to satisfy, so you'll really just be pushing air into and out of their lungs. I don't actually think this would collapse a lung. Don't quote me on that. But you would be recycling air because you wouldn't have a source of fresh air in the system, and that would eventually kill the patient. The other thing that could happen if a vacuum got created in this side of the system, if this check valve also breaks open, you could suck water up into the system and then wind up like pushing maybe water into their lungs or whatever. If the machine got itself into this state, I don't expect it to be a survivable situation for very long. One of the ways to mitigate that risk is to make sure that the check valves break open if they break. The other thing is to have redundant inputs on this side so that if one does get blocked or one of the check valves breaks closed, you still have a redundant path for air to come into the system to satisfy the vacuum. The other thing you could do is double up on check valves on this side so that if one did break open, you would still have a second redundancy. Most of these valves, the way I've designed them, if they fail, they will fail open. So you shouldn't have this problem. You might have a recirculating air problem, but it's very unlikely that these would break closed. That said, a blockage on this side of the system would essentially be the same failure state, because if you can't provide air from this side of the system, when the center section moves up, you're going to create a vacuum, and that vacuum is going to want to be satisfied in some way. During normal operation, air should flow pretty easily into this center chamber, which means that in an ideal world, you could put a vacuum relief valve here that basically says if it detects any substantial vacuum in this end of the system, it allows air input to relieve that vacuum. That said, I don't know if that part's commercially available. I don't know how to build it, and I think this state is probably a pretty rare one, but that's how ideally you would solve that situation. The second bad state isn't as bad as the first. In the second bad state, you just wind up recycling some air in the system. What happens is this valve breaks open, and so air is coming in from this side of the system, but the vacuum is also being satisfied from this side. So you're getting deoxygenated air from the patient as well as fresh air from the outside. So you're getting a mixed concentration of air in this part of the system. And then when the system starts to move down again on the inhale step, it's going to push that mixed air back into the patient, which is a bad situation. Now, again, you should have O2 saturation alarms on all your patients, so you should be able to detect the fact that their O2 sats are dropping and check the machine. Again, it's just a state you need to be aware of. One of the ways to prevent this is to double up these valves. So if one breaks open, you still have one that will protect the patient from the vacuum side of the system. So those are the two bad states that I identified. I don't think this is comprehensive, but I thought it was important to point out. If you come up with other ones, please let me know. I can record them. We can put them in the documentation. I think it's important to know what the edge cases of the system is and what the failure states look like and how to mitigate them.
Okay, so I'm going to walk you through the basic concepts of a check valve, one that you can imagine. I'm going to show you how to build one in a bit, but the concepts I show you here are going to get built on so that we can make a patient valve. So this is a cross section you're seeing of a pipe with a bushing in it and then a thin membrane. Think a piece of rubber. And the membrane is thin, so the membrane can inflate and get pushed out of the way. So as air moves this way, it pushes the membrane open and air can move out. But if you blew air back this way into the valve, it would press on that thin membrane and close it off. Now, depending on how this is built, it actually has a vacuum issue. So if there's high pressure on this side, air can move through the system. And if there's high pressure on this side, air can't move through the system. However, if there's low pressure on this side, it can actually suck air back through the system depending on the sensitivity of this membrane. So this is another check valve design that does not suffer from the same vacuum malady as the other one. If you imagine this as a piece of PVC pipe that you have a bushing in, and that bushing has a hole in the center. What you do is you put a membrane around it with holes in it. Looks kind of like an Ajax can to me. And so when air moves this way in the system, it pushes the membrane out of the way, and air can flow between this hard surface here and escape through the holes. But when you push air back through this way, these holes press up against this hard surface and seal it. Also, if you create vacuum in this section of the system, air can't be pulled backwards because you're just sucking on this centerpiece. This is a front view, and you can see that the pipe in the middle is inside those holes. So air can escape out through here and around and out, but air can't go back through this membrane that way. So I think this is actually a more reliable and straightforward check valve to build, but it does not solve the patient valve problem. So I think this is the design you should use for check valves in the system, and the patient valve is obviously the design you should use for the patient valve. Okay, so building on the last design, instead of putting it in a straight pipe, we put it in a T. So this is open to the air. Air can come through here and go out. Now, if air moves this way in the system, it'll push the membrane out of the way, inflating it, and it allows air to go out. Now, crucially, because the membrane can inflate, it also seals off this bottom section. So high pressure air from here will create a high pressure area here, but that air can't push this membrane out of the way and go out, which means that even if this is open to the air, these two sections of the system will be as highly pressurized as each other. But when pressure's cut off from this side, and you have a high pressure area here, it pushes the membrane out of the way. It doesn't move backwards, but it can move out to open air. This is the fundamental design of a patient valve. Now, it still has that vacuum issue. If you create a vacuum here, you can pull air back through. But that's simple enough to prevent. You can just add a regular check valve on this side. If you want to duplicate my test rig, you can. It looks like garbage, but it works. You take a mason jar, you take the lid, you cut a hole in it, you can put a T in, and then you put a bead of silicone around the outside. Then I punched another hole in it and put a balloon in. What that does when it's all assembled, this is a model of the lungs. So basically, the pressure can't change in this vessel. The balloon represents the lungs, and then you can push air in, you can blow air in this way, which will fill the balloon, which then puts back pressure on the system, and you can test the flow. So you'd basically reassemble this, but in this T, and then you can test it. And I have, and it works as you would expect. Okay, so I'm going to walk you through building a check valve. It's pretty straightforward. Doesn't take a lot. What you need is a bushing like this with a flat surface and a hole in it. You need a nitrile glove or some other membrane, probably works just as well, but something flexible, thin that you can punch holes in, and some tape and something to punch holes with. So you want to cut out a square about this big that can fit over the top and cover all the edges. So then you want to take that and tape it onto the bushing and then mark it
around the edge. So take that and then cut the holes out. I wouldn't use this one to save a patient, only because the holes are a little raggedy. You really want the holes to be as clean as possible. And I think while this is going to work when I show it to you, nitrile is very delicate, and I think over time it will probably fail in these areas of stress. So you notice I've taped all the way around. With this one, it's just electrical tape for the example, but you just want to make an airtight seal all the way around, keeping this slightly taut onto the face. And that's it. That's a check valve. Air can flow through this way, both being pushed and with a vacuum being sucked on this side. Air can't be pushed this way or sucked this way. Now I'm going to demonstrate it in our test rig. Just going to push it in there. And then I'm going to screw this together. So this is the test setup. You have the check valve inside. This is open to the open air, and the balloon should inflate. So there is some leakage around the balloon, but this would deflate catastrophically if the check valve didn't work. And there you go. It's a one-way check valve. And if I suck, nothing happens. One-way valve. So you would want to put this in line in the plumbing. So you would put a pipe on this side, and then a coupling, and then another pipe. Or if you could, you would just put this in line inside the pipe to allow flow one direction, but not the other direction. So that's it. There's definitely ways to improve this. You could use a more robust membrane. You could cut the holes more cleanly, but it's a proof of concept. The design works. It allows for the flows that we need and in the directions that we need them. And it's a pretty robust and reliable check valve. Now we're going to move on, and I'm going to show you how to build a patient valve. Okay, so I'm going to walk you through building a patient valve. I've designed and built a bunch of these. The one I'm going to show you is the simplest. Again, please don't use it to try to save a patient's life until you test it. I think it works. I think it's reliable, but I don't have a ventilator, so take this with a grain of salt. This is partially just a demonstration of how the valve could work. There's lots of different ways to build it, but the concepts are solid. You don't have to use exactly the plumbing I'm going to show you. You don't have to use exactly the parts I'm going to show you, but this is roughly how you could do it. Okay, so you have a 1-inch PVC-T. You have a 1-inch to IPS reducer. You have another 1-inch to IPS reducer that you have taken and turned into something like that. Now, this I've been using to prototype. It is super gnarly. You do not have to break it down to this point. You do need to take out the edges so that when it's put in here, air can flow around the outside. It doesn't have to flow through the middle. That's all. You can drill a bunch of holes in it. You can route it out. You just need some high spots to hold this thing in here. So now you have your 1-inch T. Take your regular reducer, put it in the bottom. This will go out to your PEEP, so put a pipe or something in it. Then you take your other beat up one with the holes in it, put it in one end, this direction towards the patient. Then you're going to take a standard Trojan condom and take a piece of metal with some holes in it. Actually, it doesn't have to be metal, it could be wood. Basically, it needs to be circular, and it needs to have some holes in it, and it needs to be smooth. So you're going to take your condom, you're going to trim just the end off, just the smallest amount off the end. You can take more, but you can't take less. Take your condom, then you're going to put this in the condom. Run it up to the end, like that. Then you're going to take this and you're going to fish it through. Big end.
Okay, so you fish it through, such that this is at the end. Then you take this part, you wrap it around the end, and you slide it down so that there's some tension. So you can keep pushing it this way, which pulls it through here and out around and gives this tension. The way, alternatively, it could look like this. You don't want that. So you want to push this, bring this closer, push this around the outside until it's taut. Also, make sure it's not twisted. If it's twisted, untwist it. Great. Okay, so that's a patient valve. Now you're going to probably put a coupler on this side and a coupler on this side because you're going to need to retain the condom around here some way, and you're going to need to connect this to the next thing. So what happens is high pressure air flows in here, which wants to go out the condom. So the condom expands to fill this space, blocking off this bottom port. Airflow can move past this coin, but airflow can't really move back this way. When air is going this way, it pushes the coin out of the way and it opens up this end, so air can flow out. But as soon as the pressure gradient changes, this closes back down. Also, you have some tension on the condom, which keeps it above this line. So the condom's actually slanted this way, so this is open. Also, when air comes back this way, it can flow through around the condom, which comes down and out through here. The other thing you can do to retain the condom, if you want, is you can just take another reducer and you can tuck it in here, and that prevents the condom from coming out, and it provides a circular seal, which I think is pretty strong. And it provides structural support all the way around the seal, which I think is important. That said, you need to test this. Make sure that it's smooth on the inside and make sure it's not going to rip the condom. Here's the thing about condoms. They're really strong until they get the tiniest tear in them, and then they catastrophically fall apart if they're stretched at that point. So this end isn't a problem, but the structural integrity of the tube is really important. So I'm just going to assemble it in the test rig to show you how it works. You see, even if it goes flat, still blow air through it. Put that on the top and see if I can show this to you. Okay, so I'm going to try to show you how this works. And that's a patient valve. Okay, so now that you've seen all the concepts, you have a general idea of what this thing is supposed to do conceptually, I can show you one iteration of how you could actually construct it. This CAD is dimensionally correct. It's based on commonly available parts. I've checked Home Depot, I've checked Lowe's, you can put it together. Just like everything in this project, there's probably better ways to build this. Where possible, I just standardized. So the material is 3/4 inch plywood everywhere. The threaded rod is 1/2 inch threaded rod,
The nuts are 1/2-inch threaded rod nuts. The washers are all the same. The tubes are all the same. The plumbing is all the same. So you should be able to build this with one very common set of components and one very common set of materials. So you don't need 6 different kinds of wood. You don't need 6 different kinds of threaded rod and 14 different types of plumbing attachments. Like, this is as stripped down as possible. So now I'm going to walk you through it. So this is split up into 2 pieces. There's the air pump itself, which just moves air when moved up and down. And then there's a mechanical system that moves it up and down the right amount for the right ratio and the right volume. So I'm going to walk you through first is the pump side of it. Okay, so this is the air pump. Just to get some basics out of the way first, air comes out here into the patient, and air comes back this way into the PEEP, which is attached to the side. This is not an accurately catted patient valve. This is just a T as a stand-in. Okay, so the core of this pump is a pipe inside of a pipe that moves up and down in water, just like we talked about in the concepts section. So I'm going to show you how this works. So we're going to get rid of some stuff. So now I'm taking away the pipes and the side walls. So this is the outer pipe that contains the water. And then this is the inner pipe. And this moves up and down just like that. So this inner pipe moves up and down in this outer pipe. So the outer pipe will contain water, the inner pipe won't, and this moves up and down. And as this moves up and down in water, air gets pulled and pushed in and out of these T-junctions. So you notice these are just pipes. I'm going to hide the left side here. So these are just T-junctions. This is just a pipe that goes down inside the other pipe. And so you'll have one-way valves on each of these. But basically, as this moves up, air gets pulled in. And then as this moves down, air gets pushed out. So that's it. Not super complicated. Now, you'll see that the mechanism we use to push that up is this pipe inside a pipe fork system. This is all PVC. It's all modeled on real PVC parts. And so what happens is you have this pipe guide here, and this fork moves inside of it. And as it moves up, it's going to catch these pipes, and it's going to move this up with the pipe because they overlap. Okay, so a couple more design considerations. We put these on the sides. There's limiters just to prevent some overshoot in the case of, I don't know, jerkiness in the system. We don't actually want this centerpiece to be able to jump up and out or to exceed some limit. Because remember, as high as this goes, when it falls, that's the amount of volume. So these side limiters are adjustable. And so this is more just for safety than it is for actually configuring the machine in normal use. These also provide structure on which to mount the hoses. So it's the weight of the entire center section that matters. And you'll notice that we route the hoses in kind of a clever way. So they're attached and they come down and wrap around. So they wrap up and around. So what this does is actually put some tension on the hose and take some of the weight off. Because if you add some twist here, this is actually kind of held up in tension, which reduces the weight on this center system. Because remember, this is actually pretty sensitive. And as this moves up, the hoses will kind of compress like a spring as it moves up and comes down. So it's really not super complicated. Like I said, pipe inside a pipe with water in it, and this is all just PVC. This is a coupling that obviously will move with it, but there's some CAD issues, so I can't get that to work. And the CAD is dimensionally correct, given the amount of pipe. So this is about 4 feet tall. This is actually, the whole thing is bigger than I'd like it to be, but given the constraints on the system and how buoyant ABS foam core is and how much volume you need, it turns out that this center box needs to be about 4 feet tall. Okay, so now we have a simple air pump. You can set the pressure by adjusting the amount of weight on top of this center reciprocating system, and that's basically all this does. It moves up and down, and it moves air, and if you put weight on it, it changes the pressure. Now, the smarts is, how do we move this up and down, at what rate, and at what ratio? So remember, the IDE ratio is how fast we drop this to how fast we bring it up in one cycle. So when it's falling, that's the inhale step, and when it's rising, that's the exhale step. So that's what we need to control. How fast this moves up and how fast this moves down relative to each other, and how many times a minute this whole cycle happens. Also, we need to control how much this moves up and how much this moves down, because that's the volume, right? Because if this moves up a little and down a little, it's going to move the inner pipe up a little and down a little, and that's going to move a little bit of volume of air. If we move this up a whole stroke and then down a whole stroke, we're going to move a bigger volume of air. So the next thing I'm going to show you is how we control that. Okay, so this is the whole thing assembled together. Now remember, there might be more mechanically elegant ways to do this, but what was important to me is simplicity and understandability, right? What I'm about to show you is actually conceptually about as simple as you can make this system, which means it's about as reliable as you can make this system. These two things are built independently, and they're just connected by a simple linkage. So if you find a better mechanical way to do this, you can just swap out the mechanical system. The only piece here is this mechanical linkage. That's the only way these two things are interrelated. So if you figure out a better way to move this pipe up and down in the speeds and ratios and distances you want, that's awesome. You can just pull this whole section out and do whatever you want. Okay. Okay, so these two things are connected by this linkage. So as this moves up, it's going to move this up. This pivots, but there's some CAD issues with Fusion 360, and I can't actually get it to do the linkage properly. But just know that these two things are connected, and I trust that you can keep that in your mind, that as this moves up, this will pivot, and that'll also push this up because it's constrained by this guide. So they won't be disconnected. They're actually pinned together, as you can see here. Okay, so given that these two things are pinned together, and this is going to move up, when this moves up, I'm going to hide the pump and just talk about the motion of this lever, because that's the only thing that actually matters here. Okay, so while it looks mechanically complicated, it's actually pretty simple. So this is a lever, right? That's it. So as you push down on this side, this is going to move up, just like any lever works. This is a cam that turns, right? And this lever has a roller inside of it. So I'm going to hide the front of this so that you can look into it. Okay, so I just took out half of the front of this lever. Okay, so as this cam turns, and the contact sets don't work in Fusion 360 for some reason, I don't know why, so these are going to move through each other, but just imagine that they don't. So as this turns, right, that's going to put pressure on the roller, and that's going to move down. This is a standard cam roller situation. So this is going to move, and then this is going to move, and then this is going to move. So basically, as this turns, this lever is going to go up and down, and is going to ride on that cam. So whatever the cam profile is, controls the motion of this lever. So that's how you set the IDE ratios. So we can swap these cams out. We have several in the repository. You can make any kind of cam you want, which means you can control this motion any way you want. Okay, so now we've talked about how to control the IDE ratio. Controlling respiration rate is just how fast this wheel turns. And that is controlled by whatever motor you put in this box. All this back box is a mount for this cam and a place for you to put a motor. And it's built such that you can tension a belt and you can move this up and down with screws. So you can really put any motor you need in this, or any motor you have. I don't have strong opinions. It needs more torque than it needs speed, and you need to be able to control the speed, but that's it. You could use an electric drill. These are pulleys, and so you can put any kind of step down you want that can fit. So yeah, that's it. Variable speed motor in the back controls the speed of the cam, which controls the respiration rate. The cam controls the IE ratio. So now all we need is to be able to control volume. So now we need to talk about volume. And volume is just controlled by how much this moves up and down, right? How much the pump moves up and down, and this directly controls that. So if it moves up a little and down a little, it moves a little bit of air. If it moves up a lot and down a lot, it moves a lot of air. Now, you could control this by just having a bigger cam, right? The bigger the cam is, the more you're going to push this lever down, and so the bigger the throw. But you don't want to have to cut a ton of cams for all your different volumes. So these are 6-inch wide cams with 2 inches of throw on either side. So it can at most move this up and down 4 inches. Given the calculations of how much you have to move the pump, you actually need more than 4 inches of throw. But you don't want giant cams, because the bigger you make your cam, the more off-center weight, which means this whole thing becomes unstable and difficult to deal with. You really don't want to have to cut 2-foot wide cams. That's a hassle. So that's where this lever comes in. And the lever is adjustable. So you move this motor box over, and you move this roller over. And what that means is you change the distance from the force to the fulcrum, and that changes how much this moves up and down. So this is all calculated to give you the full throw from here. If you move it all the way over, and this is calculated such that these two will always be in line, this is going to move this a lot more than it would if it was all the way at the end. So from here, it's going to move it down 2 inches and up 2 inches, and it's just going to move a little bit. But if you move it all the way over here, and it moves it down 2 inches and up 2 inches, it moves it a lot more. So that's it. You can mark this lever where the roller needs to be to get what volume, and you're in business. So now we have pressure, volume, respiration rate, IE ratio, and PEEP. That's it. That's the whole design. And while this looks mechanically wacky, a lever is as simple as you can get, and a cam is as simple as you can get, and an adjustable lever adjusts your volume. The other thing I didn't mention, but is very important about this adjustable lever, is the distance this moves changes based on where you move the roller, but the ratio of the movement remains the same. So if it's a 2-to-1 cam, it doesn't matter where you move this roller. It's always going to be 2-to-1 movement. And that's super important. So that maintenance of the ratio, regardless of the volume, is super important. Initially, I thought I could do it with just big fixed cams, and then you could just limit how far this fell every time, right? So it would just lift it a little and drop it a little, lift it a little and drop it a little. The problem is the ratio has to be baked into the cam, and it has to be continuously rising or continuously falling to push air in and out of the patient reliably. Because if it stops, that's an exhale. So it needs to be dropping the entire time to really get you that 2-to-1 ratio. If it gets abbreviated, there's no drop, which means there's no airflow. And when there's no airflow, that's an exhale. Because you've ceased providing pressure, you've ceased pushing air, the lungs are going to deflate. And the valves are going to open coming on the exhale. So you need this continuous motion of air, which is why just abbreviating the stroke doesn't do anything for you, which is why we have an adjustable lever that maintains the ratio while being able to change the volume. And that's it. You can see a whole parts list broken down in Google Sheets. All of those are in the GitHub repository. I hope someone tries to build one of these. I think there's probably a lot of different ways to do it, but this one solves all the problems in the simplest way I could come up with, and I tried a bunch of different designs. There's definitely useful, clever stuff here, and I hope you take what works and discard the rest, because that's what this was about. Anyway, thank you so much for getting this far. Like I said, the links are in the description. If you want to continue the conversation with me, that's awesome. If you have comments, again, please share them with me. I hope you like it. I hope you learned something from this, or at least, if nothing else, it amused you. It definitely kept me sane for a couple months, and that was really important. If this whole project taught me anything, it's that trying to exert some control on the situation you're in is very psychologically healthy. The alternative is hopelessness, and that's a terrible place to be. Thanks again. Stay well. We can all get through this together.